All right, we are now recording. We are ready to go. So we'll start the slideshow. So Lachesis, optimization of a handheld line launcher in a microgravity utility and rescue tasks. In many ways, kind of my defining project here at Ronin Institute. I'll go into it a little bit more. So, a little bit of the overview. This is something I've been working on for a couple of years. But line launchers are essential for maritime rescue and other types of search and rescue. Essentially a means of throwing a flotation device or grappling hook to stranded vessels or for sailors that get swept overboard. Space might require similar devices for a number of tasks I'll get into. So how do you build a device for both? Here's an example of an existing line launcher, one that uses a blank, a firearm blank, to throw a flotation device at the end of a rope. So I don't want to string anyone along here. Now, historical line launchers go back centuries. They're meant to save sailors that got swept overboard in stormy seas and tow stranded ships. Some historical examples are like the Lyle cannon used by the precursor of the U.S. Coast Guard, the Shermley rocket pistol rocket apparatus, the device you saw in the menu here. But overall, that was used by the Brits about a century ago. Many vessels today are required to carry one under international insurance guidelines. There's different types like cannons, rockets that carry rope behind them, and bows and slingshots and pneumatic versions for places where you don't want to spark, like oil or gas carrying ships. Now, commercial spaceflight is still in its infancy. There's many use cases for a line launcher or similar device in space, like EVA failure, like if someone loses contact with their spacecraft, loose modules or cargo pickup, deploying antennas, or capturing space debris. So we have less space because every kilogram costs a lot of money to put into orbit. And we have a single hand consideration because one hand's going to be on the craft typically, and the other hand is going to be using whatever tool is on hand. So if you can have multiple uses in one device, that's a big plus. So new materials offer far more promise in terms of space, pun intended again, than old-fashioned rope, like new lines, carbon nanotube yarn, as well as old-fashioned, a lot of nylon line. So is there a way to have multiple uses instead of just a one-off disposable one? We can revisit several proven concepts as well. So my design was a launcher with tethered micro rockets. Each rocket here was kind of a 3D printed one, Class D, by the standards of amateur rocketry, meaning it doesn't have much kinetic energy. So essentially, it's a 3D printed little model rocket engine packed with black powder. It's connected to 50 meters of nylon rope line, kind of abridged here for demonstration purposes, but it's kind of spooled around the front. So originally, it was a non-functional mock-up, my first prototype. I used a blank firing revolver to ignite a model rocket engine. Then I attached a fishing reel with the tape there to pull it back. As you can see, it's pretty bulky. It's right next to a standard ruler. So the first version, they have pretty bulky in terms of like the rocket and power cord at 42 grams, pretty much like Godzilla standard compared to the current one. Space constrained development, again, pun intended. So how do we miniaturize that? Especially with these big clunky model rocket engines like the A83 S-Days, the commercial ones. So I redesigned smaller model rocket engines. I wanted to realize something to make stability of the rocket and its trajectory more stable. So we made a tube launch. So it would be ignited within a device and essentially would have to burn more fuel to escape that tube, thus building up more pressure behind it and allowing it to stabilize as opposed to veer off and burning. Because it burns more fuel outside the tube, it's going to lose more accuracy. So existing devices to launch projectiles packed with wadding already exist. Very, very long time, in fact. Early firearms, especially, like in particular the Victorian percussion revolver. It was perfect. It allowed reliable ignition using the percussion cap system where a hammer would strike essentially a small brass cup full of mercury fulminate used in from after the Napoleonic Wars, roughly up through the 1860s, allowed for reliable pressure loads, and you can test multiple loads in one session. Like each chamber of these early muzzle loading revolvers could fit one of these model rockets with the wadding that is the mini packing and essentially a mini parachute to slow it down. So I could test out different loads with one device, and if things go foul, it's robust enough to essentially absorb any of the pressure. So essentially put a chute on the rocket. Also, this same system was used as an earlier version of my space debris clearance system. Load fuel in, black powder in this case, put into the chamber, and repeat for other chambers, put percussion caps on, and discharge it. So one other idea I wanted to explore was the idea of how about using a laser for reliable ignition as opposed to the janky Victorian mechanical system? Because mechanical systems, especially in space, could have far more vibration, especially on a small craft where inertia and control is far more valuable. We also wanted to stabilize rocket trajectory more and make it modular to assemble to save space. Again, my favorite pun here. So in order to add something akin to rifling, we basically had something borrowed from a lot of the hobbyist Nerf or foam dart blasters, a kind of soft rifling where we would tie strings at an angle to apply a bit of friction, a kind of an analog to conventional rifling in ballistics. So essentially, we tried two different types, fishing line and twine, to see which one would work more efficiently. So we basically had a laser system that would act via a button press that would ignite a laser diode by connecting the circuit. So likewise, the rocket was added inside this foam dart for additional safety. So if it hits something, it won't cause a lot of harm to it. So we compared the velocity with and without the soft rifling, the two types of fibers we used, twine and fishing line. Here for the soft rifling, that is, we generally use the fishing line as the stand-in for the actual line itself in space. We compared two different rocket sizes, essentially what I call the TAL and the Phi models, essentially 5.5 millimeter, and a 9 millimeter. We use the smaller one just for stability and safety purposes. This is the prototype here compared to the earlier iteration. So the average velocity was about 20 meters per second, which is the laser also had a limited or high latency, 3 seconds. So I have to pull the button for 3 seconds to make the rocket ignite. So that was largely for safety, because a pulse laser where it's all at once, again, what might be too much and cause catastrophic discharge, at least this early phase. So I used this chronograph here and measured the kinetic energy. The highest kinetic energy is about 0.127 joules of kinetic energy. So for comparison purposes, that's on par with one of these Nerf blasters. So a pulse laser could, again, reduce ignition time to an instant. The alternative rifling applied a lot of friction there, so use of roller bearings could definitely decrease that, but still have the same effect. The device is largely viable for use, though. So laser ignited rocket launch could be used in sea and space. The whole thing ended up weighing a fraction of the prior design, let's just say. We also added some metal weights like screws and such in the handle, both for legality reasons under US law, as well as for stability and gripping it. And low cost, low weight, minor improvements possible, such as the pulse laser or the roller bearings, but overall it's a decent design in its current form. Here's some references, and thank you very much.